Hello, everyone. Thank you for coming to our SiFive Tech Talk featuring Paul Kocher, who's talking about the Spectre processor vulnerability. I'm Megan Walks. I'm an engineer at SiFive. I'm leading our Freedom Everywhere platform design team. And I'm really excited to hear what Paul has to say. Usually we do these tech talks in-house at SiFive's offices, which are right across the street. But this topic was so exciting, and we've been growing and hiring so much that we could not possibly fit this size group in our office. So thank you to Paul for agreeing to talk to a larger group and come across the street to the Marriott. So I've known Paul for almost 10 years. He hired me into his company, Cryptography Research. He founded that company. He and his co-founders discovered and published the paper on differential power analysis attacks. And it's kind of a classic paper. If you've never read it, I'd highly recommend it. And then you should go attack one of your devices and see how easy and applicable it really is. And as Paul's company grew and his renown in the crypto and security community grew, his company was eventually acquired by Rambus. And after we were both there for a few years, we both moved on to different things. And I personally was very curious to see what Paul would get up to next. And I think this is the first very cool thing that Paul's done. And so thanks again, Paul, for coming. And I'm really excited to hear what this all means for secure hardware design. Thanks. And thank you all for coming, too.
Thanks, Megan. So when she calls it cool, she clearly doesn't work for Intel or ARM right now. I can just absolutely assure you of that. I'm going to actually begin with a quick raise of hands. How many people here know what a branch predictor is? Oh, right. OK, good. So that means then that I don't need to spend as much time as I normally would on some introductory stuff, and I'll dig into some of the more interesting aspects of this. So Megan already gave me an introduction, so I'm just going to, I think, just completely skip this since you already know who I am, or if you don't, you're already stuck here, so there's no way you can leave. And so I'm going to just begin by talking about two different attacks that got unveiled at the same time. So the history here was that I was looking at Intel processors, and I'll describe some of this a little bit later, and found some issues, contacted Intel, and they said, oh yeah, other people have been telling us about some other issues in our processors, and we started getting in touch with each other and finding each other and comparing some notes. So in the end, there were these two vulnerabilities that got released at the same time, and they were given different names for a couple reasons. One is that they actually have fairly different trajectories in terms of their implications for end users and for processors. Also, there were different groups of people working on each, and if you've ever worked with academics, it's kind of important who's on your paper and who's not and that kind of thing. So they wanted to have a name for the Meltdown vulnerability, and I'd already picked the name Spectre for what I was looking at. But they're both issues that arise from hardware. I'm going to use the word vulnerabilities and bugs somewhat interchangeably. People from Intel would probably prefer I use the word vulnerability. I actually think they're both involve basically bugs at the same time. So with Meltdown, what's going on is you can run a piece of code running in ordinary, unprivileged user space on a processor. And if it attempts to read from memory that it's not allowed to read from, like if you're particularly a user mode process and you try to read kernel memory, you're not supposed to be able to do that. It's against the rules to be able to read kernel memory, because then you could read all the other processes' memory contents on the machine. But what happens when that read occurs is that the processor runs a little bit ahead and speculatively or out of order runs some of the next instructions. And you can trick those into leaking the memory you weren't supposed to see. There's no involvement in any other code in the system when you're doing this, though. So it's something that is really happening between the attacker process and the CPU. Although the mitigations for it can be done just in software in a fairly clean way, because the solution there is to basically take all of the really sensitive stuff that the kernel has access to and put it in its own virtual address space instead of leaving it mapped in the user's address space, but with a bit saying don't touch this. So if you look at Meltdown, the main consequence is you're exposing the physical memory of the entire system. So if you're on a cloud machine, you can read all of the physical memory of all the other processes sitting on the machine, which is really a bad thing in practice because that violates the security separation between different processes. There's not really any customization required, so it doesn't matter what the operating system is doing or what the victim processes are or what they're doing. You're just basically dumping memory straight out. And it's mainly affecting Intel's processors, but there are also some ARM ones that have the vulnerability as well. It seems to involve some race conditions involving the timing between when security check results are available and when speculative execution starts using the results from memory reads. So primarily an Intel issue, but not entirely. But the good thing about Meltdown is we've got a software-based operating system level remediation that addresses the problem. So from a user perspective, if you're unpatched and you're in a vulnerable environment, it's an absolute panic, all hands on board to get the patches installed. And once you've done that, you can kind of breathe easily. Spectre is kind of different. It's a little trickier to take advantage of because you're tricking the processor in mistraining the branch predictors and making it do things that are more subtle, but you're exploiting permissions that were already there. So one process can attack another, a process can attack the operating system, a process can actually have code running in a sandbox inside of it that is reading things outside of that sandbox. So there's a whole lot of different scenarios, and the mitigations are super, super, super messy. And I'm going to talk about those. And I'm actually using the word mitigation rather than fix because that seems to be what the industry has coalesced around. You're not fixing the problem, you're kind of burying it and making it harder to exploit, or you're moving certain scenarios out of the threat scenario. So the other thing about Spectre is it's really a mistake in philosophy in how high-speed processors have been designed for the past 20 years. It's a mistake that if you go and you read books on how to build a fast processor, they'll tell you to go build a branch predictor that will predict things. They'll tell you to go do speculative execution, because these things all make your processor run faster. But basically, if you follow those instructions, you end up with an insecure processor coming out the other side. So that's why it's not particularly surprising that you see the same philosophy showing up in all of the sort of speed competitive processors. So the ARM high-speed cores, Intel's x86 line, AMD's Spark, Power, et cetera. These are all trying to hit really aggressive performance milestones, all using the same bag of tricks to do that. And one of the items in that bag of tricks turns out to be dangerous. And that's what I'm mostly going to talk to in the presentation this afternoon. So we've run into a crisis of performance in the computing industry in that the things that used to be giving better performance have kind of been tapped out. And two in particular I want to highlight. One is clock rates. So somewhere around 2005, we started to hit 4 gigahertz, and we're still around 4 gigahertz today. There really haven't been major improvements in clock rate that have been a driver of performance. Another area where there have been also some improvements, but not enough to keep pace with the needs of people wanting ever faster machines, is memory latency. So the time it takes to get information from memory has not kept pace with processors. And so given these two sort of fundamental electrical engineering limitations, people have devised some pretty creative ways to work around them, which are the things that I'm going to exploit from a security perspective as we go along here. So the way that we deal with the memory latency problem is we use caches. So we put in, we have our large amounts of relatively slow memory that might take 200 or 400 clock cycles to actually get something out of, but we can have some much more expensive per bit, much faster memory close by, which can give us information much faster. And so we put the things we use often close by, and then we'll fall off to the slower memory later. And I'll talk about a little bit more how that works in a minute, because it matters for how these attacks work. The other thing that we put in processors is speculative execution. And what that basically means is that when the processor isn't sure what's going to happen next, rather than just sitting around, it's going to make some guesses and run ahead and only keep the extra work if those guesses are right. I'll talk a little bit more about that also as I go along here. But the Spectre vulnerability, in the most common form, involves an interplay or a combination of issues that arise from the use of caches and speculative execution. And I'm going to describe sort of the classic examples of the attack here. There are a whole bunch of variants. So if you're trying to protect a system, going and dealing with the classic version doesn't mean that you actually protect against the variants. But my goal is to explain how the attack works, and then I can talk maybe at the end a little bit about other ways that the attack can be implemented. So I talked a second ago about memory caches. So the idea of a memory cache is really simple. You've got your 16 gigabytes of memory or whatever size you have, which is slow, and you've got this little bit of really, really fast memory. And one of the observations that people made many, many years ago is that processors tend to, when they're actually running normal software, tend to use a small number of memory locations really often and lots of the memory is seldom, if ever, used. So if you can keep those things that you need really often somewhere where you can get to them very quickly, you're going to end up with a dramatic performance improvement over waiting for this external memory. So when, for example, the CPU wants to read something from an address here, and so here my address is C0708, what happens in the hardware is that this address gets used to pick basically a bucket or a little tiny set of maybe 4 memory locations where there might be a cached copy of this. The processor looks there, and in this case, it's got a cache hit. The memory at that location is in the cache, and so the read can be serviced very, very quickly. It doesn't need to go out and wait for the delay associated with going to external memory. But for other reads, this one here maps to this cache set. It's not in the cache. So the processor is going to go off to the main memory, which is really slow. And there's going to be a significant delay while that happens. But finally, the result will come back. And the processor will throw away one of the things in its cache to hold the value that it retrieved, because there's a good chance it's going to want that again later. And I'm glossing over a whole bunch of details like different levels in the cache hierarchy and different cache replacement policies. But typically what happens is this new value gets stored for subsequent reads so that when the processor later wants that same value, unless it's been evicted, it'll be there and can be serviced quickly. Now, something to note about this, though, is that the fact that I did a memory read changed the state of my processor. Now, that's kind of non-intuitive. When you think of reading a book, you don't underline the words that you read with your name and exactly when you did it. Or when you go and read memory, you think of this as a passive operation that leaves the system in the same state that it was in before. Now, from the perspective of the quote architectural state of the system, what actually happens if we ignore timing, that's actually right, because whether or not this value is cached here won't change the data that I get when I do a read, but it will change the timing. And one of the things that the Spectre attack is going to take advantage of is the fact that when these memory reads occur, they still leave something that's detectable later on in the system state, in particular, whether or not a particular value was brought into the cache. So speculative execution, sort of push the cache onto the stack. We'll come back to that in just a moment. So speculative execution is used as a way to improve performance. So if you think of a program as a series of steps, very often the processor will run into a step where it can't instantaneously service that. In fact, that's true for when you have a pipelined processor. It's actually processing different instructions at multiple instructions at the same time. But if a step in that process stalls, for example, if it reads something from memory that isn't in the cache, there's going to be a big, long wait before that instruction is able to be fully retired or completed. So if you don't care about performance, you're just going to sit around and wait. But if you do care about performance, it's absolutely toxic to be sitting around doing nothing for 200 clock cycles while you go wait for something to come back from memory. So the solution to this problem, where I'm going to use solution from a performance perspective, not a security one, is to guess what you're likely to see and see whether that can let you proceed on with execution in the program. So if the classic example I'm going to use here is I'm going to compare a value that I know against something in memory and decide whether to branch somewhere different on the basis of that comparison result. So in that case, the correct path that the processor is going to take isn't going to be known for a couple hundred clock cycles. However, most branches do the same thing over and over again with occasional exceptions. So if I have a loop, I might go through the loop 100 times and then not iterate again. Well, that means that 99% of the time, that jump instruction for my loop is going to loop backwards. And so what the processor has is inside a branch prediction circuitry where, given a particular branch, it'll make a guess as to what it's likely to do just based on historic behavior, not on the basis of the actual correct outcome for the given program. Now, from a programmer perspective, this means that the processor is doing things that you never asked for. It's making guesses about what you might want and going off and doing actions on the basis of those guesses. Now, that's okay from an architectural perspective, where architectural means basically non-security in this sense, because if the processor guesses wrong, it can go back and pick up where the mistake occurred and then do the correct calculation. So the mistakes are completely hidden. It's going to throw away the results of those incorrect calculations from an architectural perspective. but things like changes to the cache don't get thrown away. And that's where something that starts to look, that initially seems somewhat innocuous, starts to become a real problem from a security perspective. So here's an example of just two very simple lines of code. We're going to take a variable x, check to see whether it's in bounds. We'll assume everything here is unsigned, so don't worry about the negative cases. And if it's within bounds of array 1, then we're going to go look something up and do a couple operations with that. This is exactly the kind of thing you would regularly see in that a security-focused programmer would write. They want to make sure that you're only going to go do this operation if x is within a valid range, and if it's not, you'll go handle it somewhat with an error or something else. So here, let's explain a couple more things in our scenario. We're going to assume that the attacker is going to supply the value of x. We're going to then look at what happens when this thing gets run with a processor with speculative execution. So if the value of array 1 size is off in memory somewhere, it's not in the cache, which can occur either because the attacker caused it to get removed from the cache or just because it hasn't been used for a while or something else happened to bring some things into memory that caused it to be evicted. Well, then the branch predictor that's going to basically run the compiled version of this is going to see a compare operation followed by a conditional branch, and it's not going to know the outcome of that branch for quite a while. But if you're the attacker, or even in legitimate operation, most inputs, like the last few that we're seeing, are going to have valid values of x that are in bounds. So the branch predictor here is going to predict that the if statement is going to be true, even though it's not. So what happens is the speculative execution wants to get a jump on the real calculation here, and it goes off and it reads the value array1x with this way, way, way out of bounds value. So internal to the processor, it's going to take the value of x, it's going to add that onto the start of array 1 to find the memory address that it's going to read from. And for anybody who's ever exploited a buffer overflow attack, you'll know that if I can add a 64-bit value onto a 64-bit pointer, I can make that go absolutely anywhere I want in memory. It's not like I have to pick just 1 or 2 bytes past the end of array 1. I can go absolutely anywhere, read absolutely anything that the process was able to read. Because speculative execution minus the meltdown issue does follow the same rules limiting what processes are allowed to read from. So speculative execution goes off and reads this value of array 1x. And the attacker can choose a value of x that reads, for example, a byte of a key that they'd like to discover. So the next thing the CPU then does is it takes this key byte that got fetched, and it uses that to form the index into array 2 and does another read. Now, the second read is the interesting one in some ways because this read is going to modify the state of the cache. Remember before how when you do a memory read, you change the cache state, and in fact, what you bring into the cache gets held there for later. Well, this means that one location in array 2 is going to get brought into the cache by the speculative execution. And which one it is determined by the secret byte here. So once this is speculatively executed, we've now got a modification in our cache state where what that modification was reveals the value of the key byte that we're trying to obtain. You might wonder why there's a multiplication by 256 there, and that's helpful because it means that every possible value for the key byte will map to a different chunk of memory in the cache. So caches typically have a 64-byte, work on 64-byte pieces of data. So if you map this to something which is of a larger size than that, then you can uniquely figure out the bytes. There are a variety of other ways to make the attack work that I'm not going to go into where that may or may not matter, but just conceptually this makes this the easiest to understand. So, so the CPU then is going to recognize that it made a mistake. So it made the branch predictor predicted that the if was going to be true. It was really false. Eventually, the data for array 1 size comes in, and the CPU is going to throw away all of the modifications to its register state. And if there was even a write to the value of y in memory, that would have been buffered and not saved. And all of that gets thrown away. But the change to the cache here does not get thrown away. So all the attacker then has to do is later, perhaps much later, come along and check to see which value in array 2, or which I here, had a value that was brought into the cache. And that's really easy to tell because if I read array 2 location 5 times 256 and it's not cached, it's going to be really slow. If it is cached, it's going to be fast. So I'm going to see an order of magnitude speed difference between the array2 location corresponding to the secret byte that I'm trying to leak versus the secret byte, versus all of the other possible values for that byte. So when you do this, the sample code in the paper reads about 10 kilobytes a second, and I made no attempt whatsoever to optimize that. So you can do this quite quickly. I suspect people probably get this around a megabyte per second leaking out. But when you're dealing with a cryptographic key or some other piece of sensitive data, the difference of whether it's 1 byte per second or a megabyte per second is kind of a rounding error. You've got a fundamental violation of your process separation or your security sandboxing going on here. So this is probably going to be boring for those of you who know what branch predictors are, but I'm going to give just a real-world analogy for the two of you that don't, and don't feel embarrassed. I had never dealt with branch predictors before really poking into some of this stuff either. So we're going to pretend that we've got a Bob the CPU who is performance obsessed. He's constantly afraid he's going to lose his job if he can't run twice as fast every 18 months. And he's a researcher for a top secret project, and he gets research requests in. He immediately decides to start working on them because he doesn't know if they're authentic or not. It takes a while to find out whether they were actually things he was supposed to do, but he's going to throw away his research results and never tell them to anybody at all if he can't authenticate the inquiry. And Mallory, our evil attacker here, wants to know a secret that Bob has access to. So Mallory asks a question of Bob. What color is the book whose title begins with the first letter of the secret? Bob, being a faithful researcher, goes off to the library, checks out the book, looks up the color, writes it down, and then throws away the piece of paper that he wrote it down on. Mallory then asks the next question, and Bob here is a CPU. He remembers his pipeline depth is a few nanoseconds here. So he doesn't remember that he's been asked some strange questions before. The next question comes in: what color is the book whose title begins with the second letter of the secret? Bob goes off, checks the book out, writes it down, then burns the slip of paper that he wrote it down on. And this continues. And at the end of this, the question is, what can Mallory learn from the series of titles that Bob accessed? And clearly, Mallory doesn't care about the color of the book. In the same way that Mallory doesn't actually care what was in array 2 or what the result of that was or what happened in that calculation. Mallory just wanted to find out what change happened to the hidden state of the system as a result of the query that was sent in. And here the query is asking to look at books as opposed to reading things from memory. But clearly, Bob's leaking out his secret to Mallory here, because assuming Mallory is able to get the records from the library. So to give an example of how this works from a kind of a practical attack perspective, I wrote a piece of code in JavaScript, and this was the first time I ever used anything in JavaScript, and I kind of hope it's the last. It's a pretty gruesome language, but it was an interesting learning experience looking at what goes on under the hood there. So the sort of sandboxing philosophy for JavaScript is that you have pieces of code that are coming from particularly nasty sources, like random advertisers on the internet, and it's pretty hard to think of a source worse than that. You're going to take this code and you're going to compile it into executable instructions on your computer and run them. But the job of that compiler, the JIT, the just-in-time compilation system, is to make sure that the output code can never do anything that violates the security requirements that have been set forth. So there are certain things that the language does to make it so that it's possible to enforce these constraints, like you don't have arbitrary pointers, and array accesses are always going to be checked by the JIT as part of the, it'll make sure that the code that's produced can never do anything outside of the bounds that it's supposed to be able to access. But as an attacker, from an attacker perspective though, I've just shown you a couple slides ago that you can violate bounds checks. And so to do that here, I asked the question of could I write JavaScript code where the compiled result would involve a bounds check that speculative execution would just blast right on through and let me read arbitrary memory. So I ended up writing this piece of code, which looks an awful lot like the example I showed you before. This is basically reading from the first array. There's then some things that enforce some limitations on the result of that so that the JIT doesn't have to output a whole bunch of stuff that ruins the performance and messes things up. And then it goes and reads from a second array. And so if we look at this, the index value here is a thing that's going to be in bounds when I'm training the branch predictor, out of bounds during the attack pass. I have a length value, which actually in some code before this I accessed so that it was brought into a location where it was quickly available, but not too quickly available, and I could evict it. So there was some junk code before this that I had to tweak to get things just right. It then does an initial out-of-bounds read. It's funny, or zeros are a trick that JavaScript programmers use to tell the compiler that it's a integer as opposed to, for example, a string. So it gives you more efficient output. This then is a mask that keeps the JavaScript compiler from worrying that I'm going to be reading something out of bounds in my second access. Here I use 4096 instead of 256 as the thing to multiply with for just memory architecture reasons that don't matter a lot here. And then I do a second memory lookup. So when this thing gets, there's some little details about how mistraining gets done and how evictions happen. You can read about these in the paper or talk to me afterwards if you want. But basically though, each of these things can be worked around. So like to cause evictions, you don't have access to this nice simple instruction that causes things to be thrown out from the cache. But if you read a bunch of things at 4096 byte increments, it kind of has the same effect. And likewise, you don't have a good timer in JavaScript. They actually took the nice timers away because people were abusing them. But it turns out that they allow multi-threaded operation, or at least they did. They took that feature away after the Spectre paper came out. But the multi-threaded operation means I just start one thread that just counts, and reading the counter value from the other one gives you a perfectly good timer. Making the timer inaccurate does not work very well as a countermeasure, though, because if you just think about it, the difference of an order of magnitude speed between the case where something's cached or not cached, I can always just repeat that and average over a number of iterations and figure out whether or not I'm what the byte is. But people have been making their timers less accurate as well. So this is the disassembly that actually comes out from that code. So you'll see there's a compare operation. If the index is larger than the length, it bails out from the next instructions. It goes and basically looks up the index of the next thing to read, and then goes ahead and checks. I already had an AND instruction that told the JIT that I couldn't possibly be out of bounds, so it didn't do any more bounds checking there. And then it goes ahead and does the read at the end here that leaks the information. So that's the basis of sort of basic form of what I call the conditional branch variant of Spectre. The Google researcher who independently discovered these issues, and he wrote his write-up completely separately from mine, called it a variant 1 of the attack, but it's the same concept. There's another variant which is actually a lot nastier, which involves indirect branches. So there are lots of times, so in the case of a conditional branch, it's like you're driving on the road and there are two possible destinations where you can go left or right, or basically the next instruction or some other instruction. Indirect branches are different. For those, you can go absolutely anywhere. It's like a thing that will teleport you to any house you want in the city in just one instruction. And you see these things showing up in code in lots of places, like if you do a switch statement or a return after a function call. The return instruction can take you anywhere because it needs to take you back to wherever the caller was. And there may be hundreds or thousands of different places that a given function might be called in a complicated program. So you need to be able to go back to whatever that location happened to be. So, but now from an attacker perspective, this means that I don't just have two possible things I could choose for my victim to do. I can send the victim absolutely anywhere that I want. So the idea here is that I'm going to pick a branch in the victim that I'm going to redirect speculatively. And the word speculatively is important here because all of the incorrect calculations are going to get thrown away. I'll then pick the destination where I want the victim to go, and I can pick basically anywhere I want that the victim would normally be able to execute from. And I'll pick some code there, which I call a gadget. This is the same idea as kind of a gadget in return-oriented programming, where you have some software that's already present that is going to be executed in a way or at a time that isn't normal for correct program execution. So I'm going to leverage the little bits of logic already in a program to use that to attack the program itself. So the attack then ends up with basically 5 stages. I'm going to mistrain the branch predictor so that when the victim runs a perfectly innocuous indirect branch, it's going to end up being speculatively sent off to the gadget. I'm going to make it so that there's going to be a cache miss that will occur when that indirect branch occurs in the victim so that it's going to be, the processor is going to speculatively execute for a nice long time. I'm going to invoke the victim to make it then go do this operation and have this occur. I'll then detect some changes in the cache state or some other covert channel in order to be able to find the leaked information, and then I'll repeat this over and over again. So in the case of one of the implementations I did, I was looking at a Windows machine program, and it turns out that when you call the sleep function, the first thing that happens is that there's a indirect branch in the DLL that implements that jumps to the code that implements that. So I decided that I was going to hijack that jump, and it turned out in the victim code that I was looking at, the EBX and EDI registers happen to have things that the attacker could control. And it's really common when a piece of code that receives input from the outside goes and does something, some of the data from the outside will be sitting in registers. And in the case of the sleep function, it's required to preserve the state of those registers, which it correctly does, but the values sitting in there are something that are basically left over from calculations in the program called sleep. So there's this jump at the beginning. The location it goes to will change every time you reboot your machine because of a technique called ASLR, address space randomization. So you won't see exactly that destination, but that's kind of the construction of what appears there. So I found a gadget. I then searched for gadgets that would let me use EBX and EDI to make arbitrary leaks. And I searched through basically just the standard Windows DLLs and actually the subset of those that a very minimal Windows program loads. So I took the sort of most minimal Windows program I could write, saved out the pages of memory that were the things that were in its working set, and then searched for nice gadgets there. And I had a few megabytes of code to search through, which is plenty. There were lots of options. I just happened to pick this particular one, which takes the value in EBX, adds EDX on, which in the victim happens to be 3, some constant that I don't care about because I can adjust for it, does a read there. So this is like the first step in my example earlier where I'm reading something that I wish to leak, and then I've got a second read where basically the result of adding this value onto EDI, which I also control, gets used as an index to make another memory read. And given the control over EBX and EDI, I can basically then control which location the victim is going to leak the contents of, and I can also control where in memory I align my second operation here. And so I pointed this second thing at a chunk of shared library code, because when the victim reads from that shared library space, I in my attack process can also read from the same area. And it turns out that those map even to the same physical memory, because we wouldn't want to waste memory on a system. We want to have one copy of the same shared library for everybody. There was also another gadget that I used to actually find the locations of things. And that gadget let me break ASLR in a fairly straightforward way. There are other ways to break ASLR, but when you've got a hammer and the hammer that you're using is speculative execution and you want to break something, you use that hammer instead of other hammers that might actually be more well suited to the job, but it worked just fine. So I went through you go through this process and you can trick the victim into running the gadget, even though this victim code would absolutely never jump from the beginning of the sleep DLL off to this random, I think perhaps even in misaligned sequence of instruction bytes that happen to be sitting somewhere in ntdll.dll. I have no idea what this code or what these bytes are supposed to do, but they work. I don't care as the attacker. I just find something I want the victim to run. The victim runs it. And also, one other really interesting thing is that normally for return-oriented programming, you actually have to get control flow back again after you run your gadgets. But here it doesn't matter. The processor is going to run this speculatively, realize it made a mistake, and it automatically takes care of getting the victim right back to where they ought to be. And so it's much easier in some ways to do this than return-oriented programming. And in some ways it's a little bit trickier, but it's probably a pretty comparable kind of attack complexity overall. One note that is a little bit non-intuitive to people who haven't dealt with virtual address spaces. So every program running on a computer has its own address space. And what that means is that, for example, memory location 300 for one program may point to one piece of memory. Location 300 for another program may point to a different piece of memory. And the branch predictor doesn't have any idea which program is actually teaching it. It just looks at the virtual addresses going by. So when it sees that there's a branch from virtual address 300 to virtual address 400, it just assumes that regardless of which program is running, 300 is likely to go to 400, and it makes future guesses on the basis of that. So from the attacker, this means I just need to make things that mimic the victim's series of branches well enough that the branch predictor is going to apply predictions based on my learning over when it does speculative execution of that victim. And there are a bunch of other details that I won't go into here, but for example, while it's learning, it often only pays attention to some of the low bits of the address. So on this laptop here, it only really cares about the low 20 bits of the address. On AMD machines, and they're vulnerable to both variants of Spectre despite some initial statements to the contrary, they look at the low, I think it's 12 or 12 bits of the address. And there's some other details about how the branch predictor decides which predictions to apply, but all of this stuff you can trick relatively easily by just mimicking the victim behavior. And only and even underneath that, you only have to mimic the parts that the branch predictor pays attention to. So there are sort of several examples of implemented attacks using this. One that I wrote was one process running on Windows stealing a key from a different process. So I wasn't using any operating system attributes at all. It's just one process attacking another. The Google Project Zero researcher who discovered this did an implementation where he attacked the kernel by leveraging just-in-time compilation capability as part of the eBPF, which was originally the Berkeley packet filter, but it gets used for things other than packet filtering. So there's a really fast way of doing some filtering stuff in there that lets you actually create some bits of code, which meant that he didn't have to find gadgets, he just created them himself. So what do we do about this? I think I can tell you my afterlife is not going to be pretty if I'm responsible for the work that people have had to do here. There's some messes. So all of the mitigations here are super messy. None of them are cost-free, and they're all heavy in complexity, heavy on performance impact, heavy on engineering time, heavy on stability issues as you try to go and do surgery on fielded chips through microcode updates and that kind of thing. So first of all, a whole bunch of CPUs can't be fixed at all. So microcode updates are not available on most non-x86 platforms. So if you've got one of those in a product that's used in some vulnerable way, you're kind of in trouble. And some ways, Intel's been getting a lot of criticism for their mitigation attempts, but it's worth pointing out that at least they're making attempts and there are some options there as opposed to just absolutely nothing that you can do whatsoever. Okay, so before you get really upset that you're dealing with microcode updates, maybe you should be glad that you at least have the option to go through this mitigation experience. So one approach is, so both Intel and ARM have retroactively defined instructions that work on legacy processors that have the effect of being speculation barriers. So in particular, the L-fence instruction is the cleanest one on x86 platforms, where if you do, for example, a conditional branch and then there's an L-fence, the speculation won't run past that. So the mitigation here is conceptually really simple, but in practice absolutely impossible, which is you just stick an L-fence on every single path of every conditional branch, and that variant of Spectre to a first order approximation goes away. It means you have to recompile and replace all of your legacy code because you can't keep using, and if you have one that you miss somewhere, you're dead. But if you did theoretically do that, you'd address the problem, but you'd also absolutely massacre your performance. I ran a test where I took a simple SHA implementation, one of the hash functions, and put L fences in just one of the loops, and the performance was less than half of what I started with. So that's not necessarily practical from a performance perspective for a lot of applications, but it's conceptually straightforward enough to imagine that your compiler could put these in everywhere. Now, there's a possibility that the compiler can only put them in where they're needed, and there certainly are some cases where they're not, but I'm skeptical there's any Goldilocks solution where you've got enough in there that you're going to fix that variant of Spectre, but not absolutely unacceptably harm your performance. But that's an open question in static analysis. There are some compiler attempts that don't comprehensively insert these, but that's not very useful because if you think of an exploitable conditional branch as kind of like an open door in a building, going and shutting 3/4 of the doors and locking them with really great deadbolts doesn't really matter if you're an attacker. It's the question of whether you've got all of them. And you know, a complicated program, I ran a quick scan on my Microsoft Office install and counted 24 million conditional branch instructions. So you know, you're not going to manually go through all of those to figure out which are exploitable in which situations. So that's one kind of messy area of mitigation. There are some ugly pointer tricks. So for example, some of the WebKit folks are doing some things where they're basically corrupting the pointers in memory so that if they get used in the wrong way speculatively, they won't be uncorrupted in the right way, and then you can make it less likely that you're going to end up leaking something that you shouldn't. It's got a pretty significant code impact, but that kind of thing might be usable. Is usable, for example, in a JavaScript JIT, but you're not likely to go do that in some complicated legacy C program. There are other things you can do, like you can AND a value onto your index that will tend to clamp it down to an acceptable range, and at least right now, processors don't seem to be speculating the results of AND operations, although I suspect if people do this countermeasure a lot, some brilliant engineer is going to go realize that there are lots of AND operations going on that don't do anything and build a speculative solution to just run right past those. So, and I'll talk about this in a minute, there's no guarantee that you have as a programmer as to what terrible things the processors will generally do to you. So there's a big gap between a processor maker's view as their architectural responsibility and what software developers assume about the hardware. And this is an example where as you try to build mitigations, you may well find that those are unsound on future devices or on some of the devices that you didn't test on. The situation for the indirect branch variant is independent. You've got a different set of mitigations there, and those are also just incredibly gruesome. So there's some new bits that are being created by Intel and AMD through microcode updates that regulate the learning and usage and state of the branch predictor and can be used to sort of selectively nuke it at certain points in time. Those aren't accessible currently from user mode code, so it's not clear that that actually works or how that will work for protecting user mode processes. But again, super messy there. And there's also a sort of another hack that Google proposed called retpoline, which works fine from far as I can tell on Haswell, but on Skylake, it predicts returns from functions and falls back to the same mechanism as indirect branches when a certain buffer is exhausted. So again, not a sound countermeasure in terms of always working everywhere, although there may be some microcode updates that again make that more sound on processors that have it. So we have this really messy set of things that are being done, and well, I don't want to be critical of people who are doing the best that's possible given a rough hand. It's not a pleasant situation for any of the folks that are trying to write compilers or kernels or JITs or web servers or database systems or cryptographic code or any of the stuff that's potentially affected by all this. One countermeasure I thought was really funny, though, is somebody took Doom and implemented it using only move instructions. There are nothing else here. The loop it's all one huge loop, and at the end there's an exception that gets triggered, which sends it back to the beginning, and it just runs through this loop of move instructions, and the power of the move instruction on x86 processors is sufficient that you can build Doom with absolutely nothing else. One frame every 7 hours, but you know, some of the countermeasures have a performance impact. We know that. Okay. So I was touching on this a second ago. There's a big gap between what hardware architects view as their responsibility and what people rely on from the hardware. So if you look at the definition of what a simple add instruction is supposed to do, the architecture document is going to say basically that it will correctly load the value in EBX and at some later point in time that will show up in RAX, which will be available for all of the instructions after that. And maybe some other cases describing what happens if you have an exception that gets triggered. But there's nothing that, for example, prohibits this operation here from modifying the cache state however it works, however the implementer wishes. There's no requirement that the timing be consistent. There's no requirement that it doesn't just automatically reveal all your secrets to an adversary through some, for example, side channel, because the architecture just describes that given this state of registers at the beginning, this piece of code that runs, and even that code has some sort of assumptions about it that you're going to see a particular outcome at the end. But if you're worried about the microarchitectural leaks that can come out of this, there are all kinds of other things that you care about, like what is the computation time? Is that going to vary? It probably won't with an add, but it might. Maybe you're going to trap this, and if the top bits are 0, run faster than if they're not. Maybe there'll be some change in the cache state. In fact, very likely there will be, because the way this instruction works, it's going to read the memory from location in register BX and add the result of that onto register RAX. And you may have timing impact from other threads. Maybe this will use the ALU in some way that a hyper-threading program that's running on the same core is going to have different ALU availability and reveal something to you. Or maybe there'll be some analog effects. In fact, Megan talked at the beginning about the work that I and others have done with differential power analysis, finding that the power consumption and also the RF emanations from chips reveal an enormous wealth of information about what's going on inside. So does the architecture assume that the adversary has a coil of wire next to the chip, or can read an analog value from the sound card, or see the power consumption of the chip as indicated by the thermal temperature going up, causing the fan to turn on? Because you run a lot of high power consumption instructions, that starts leaking in all kinds of interesting ways, and we have no guarantees about any of this. And so the core issue here is that the platforms that we're using were designed for performance and not for security. And we don't have any guarantees really that the code being run today is secure on the platforms we have today. And we have absolutely no notion about what may happen when running on future chips that comply with the architecture in terms of the backwards compatibility requirement, but may have different microarchitectural side channels. And the other consequence of this is that as you're trying to come up with countermeasures, the fixes that you're going to make to these kinds of attacks are going to be based on some set of kind of unknown assumptions. Like, I can run some code and not observe any timing variations in my add instructions, but that doesn't tell me that that's even going to be true on my own single machine that I'm running on. And if I fix some problem, I may create some other ones, because there are lots of things that can happen. Like if speculative execution reads from a particular location in memory and a particular row is now selected, what are the implications for the next read? If it's from that row, is it going to be faster? I don't know, and I have no documentation that gives me any clue about it. All I can be doing are kind of these ad hoc experiments, just trying to figure out what a given machine does to me. So some implications here for CPU vendors. There's no Goldilocks solution here. Everything you do is going to be bad, and you're going to be criticized for it. And I'm going to be one of the first to make some of the criticisms, since I don't have to go build CPUs. You can be fast and dangerous. We have that today. You can be safe but slower. You can turn off speculation completely, or try to constrain it in various ways that hurt performance as little as possible, but give speculation in the places that you think it's maybe okay. Or you can do absolutely the worst possible thing and punt a giant mess off on software programmers who have absolutely no way to deal with it. So if you're a software programmer and somebody tells you, put L fences on all conditional branches that might be exploitable, and you have no way of knowing which those are, because you've got 24 million of them, and if you miss one, you're going to be blamed. Well, okay, you punted to software, but you didn't actually give a realistic, reasonable performance way for that software developer to solve the problem. In general, these things also aren't testable from a software perspective. It takes sort of creative thinking to figure out how to read from these side channels, but the architectural effect is that these incorrect calculations are simply thrown away. And while it may have some impact on exactly the number of clock cycles consumed, programmers, when they're off writing a program in JavaScript, are not thinking about exactly how many clock cycles each line of code they're producing is going to take, and even more what the impact of their things will be on some attack process that might be running in the same system. So there are a bunch of areas where CPU vendors need to be kind of asking questions, including ones of what can we do to make architectures that actually are built so that software developers aren't assuming on things that are undefined in the architecture, because that's what a secure architecture would have to look like. Questions about, what are the researchers' agendas here? These problems should have been found 15 years ago. They probably should have been found by CPU vendors, not by, me in my spare time, since I quit my job and didn't have anything, no gainful employment, so I'm off causing problems. They should have been found by people whose job was to do that. Google folks were also working basically blind. They were looking at behavior of some code they were looking at and saw things appearing in the cache that were curious and tracked it down. And so wasn't coming from the people who could have quickly got questions answered like, hey, how does branch prediction actually get implemented in a modern processor? And then there are also some significant questions around roadmaps, because the way you squeeze more performance out of a clock cycle in a processor is by getting more work done in it. And speculative execution is one of the critical ways people have been leveraging, or techniques people have been leveraging to get better and better performance. So we don't have a good sense right now of what happens to some of these roadmaps if some of those gains are taken away. And then there's some other risks around psychology and customer perception and brand. Like, we're not used to having security vulnerabilities that aren't fully fixed by the time we hear about them. We're used to reading, okay, there was a bug in Windows. Here's the patch that was released last Tuesday. So long as you've installed it, you're okay. We've got, this is kind of the Meltdown situation. At least you can do something and sleep well again. But when you have something where the mitigations are messy and incomplete and you don't get that same level of comfort. Now, in a second, I'm going to talk about kind of the absolute effect and risk, though. I don't want to pretend things were great and they're terrible now. Security was in a really bad state before and is still in a bad state. For software developers, there's a huge pile of work to do here, and there are currently virtually no good tools to enable it. So there are things that require source-level changes really throughout an application, like how you're going to deal with your different branches, what modes you're going to be turning on for branch predictor state if you're writing, for example, a kernel device driver, tons of legacy code. Just getting the libraries that are part of that come with your compiler or your SDK updated to have L-fences, it's going to be an arbitrarily long time, because right now there are some tools that don't do a great job there and none that I would view as satisfactory. There's a lot of code that's affected. Basically anything that receives untrusted input and is processing that is at high risk. There are theoretically other scenarios that could be a problem, but the main thing to pay attention to now are things like kernels and drivers and databases and web browsers and all of this kind of stuff. But that's a lot of code. For IT departments, besides the install the patches as they become available, there's also some things you can do around trying to segregate workloads so that you aren't, in the worst case, hyper-threading something with your really important secrets in it, along with something that an attacker can control. So that's the most dangerous situation. The sort of medium one is where you're mixing on the same system data, and then the best case is where you've got dedicated machines. So for systems where security is really important, I'm thinking of scaling at the machine granularity rather than at, for example, the virtual CPU granularity. But there are some huge unmet needs here. We do not have CPUs and hypervisors and compilers and just the whole tool chain needed to be able to be confident that software running in one security context can't compromise software running in another security context. So we look at winners and losers. Intel, AMD, ARM, sort of different stakeholders that have different impacts here. I think that the one I'll probably highlight here, since SiFive graciously organized this presentation, and I had this here even before they invited me, so it's okay. Don't view this as market, but this is actually great, I think, for open source CPUs and where there's a lot more transparency about what's going on. As people are asking questions around second sourcing and alternative architectures, environments where you aren't encumbered through either licensing terms or opacity in designs about understanding and being able to make sort of reasoning about the security properties. You get the best bang for the buck out of open source environments. It's also great for researchers and kind of frightening for processor companies. If you, before the embargo prematurely ended on January 3rd, there were a handful of people looking at CPU security issues. There are now probably an order of magnitude more that I'm aware of. So if you assume that the rate at which bugs are found is not limited by the number of bugs, I use a big reserve of them, but instead limited by the number of people looking, I would expect that we're going to see more vulnerabilities in hardware showing up over the next months here. But now, it's super important for me to use the RISC in context. This is also the first time I ever got to use the poop emoji, so I just have to let you know that. I mean, software security and computer security generally were an absolute mess before. And piling a couple new vulnerabilities on that are somewhat tricky to mitigate probably doesn't change the overall risk profile in any appreciable way. There will be attacks that use these techniques, but there will be lots of attacks that don't. And so while they matter, and the idea isn't that you can just go off and ignore them, it's also not something where we had this beautiful, pristine building with no problems before, and somebody has now broken all the windows. They were all broken before. But the psychology is interesting here because we're not used, as I mentioned briefly before, to having unfixed risks. We're used to having ones where we know exactly what we need to do. And even if what we're doing is putting just a very little tiny Band-Aid exactly over the wound, you know, we've been slapping thousands of these bandages all over the wounds. We now have some that are not fully mitigated, and well, there's going to be lots of things going on that will make the attacks more difficult to exploit. And in some cases, there may even be full mitigations for certain scenarios on certain pieces of hardware. It's going to be a messy, sort of decade-long slog here, not something where we have a nice, quick, clean solution. One other thing that I wanted to talk about kind of as I wrap up here is the ethics and problems around hardware flaws. So we know what to do when we find a software bug. You notify the vendor who makes the program. They come up with a patch. They need to put the patch out on a reasonably timely basis, and at some point you can talk about what you found as a researcher. When something involves hardware, that process doesn't work very well. And this is the second time I've been through a major hardware vulnerability embargo process infecting lots and lots of fielded devices. The first was with differential power analysis, which compromised essentially all of the smart cards that were in the field at the time. In both cases, you know, it really wasn't clear how long the embargo should be. In both cases, it was actually leaked to the press that dictated the end of it. In both cases, most of the parties who had a major legitimate need to know were completely in the dark until the problem came to light, because if you told everybody who had a real need to know, that would be more people than can keep a secret. And in fact, the trade-off between letting people know and maintaining some semblance of secrecy, in both cases, it was kind of that trade-off that caused the final disclosure to occur. There are also a lot of moral questions. Is it moral to let only the big major vendors know and not let the smaller ones know? Which countries are supposed to know? What do you do about attacks that might be going on from people who discover during the disclosure process but might use it for offensive purposes? And there's a lot of conflicting agendas that get involved. So, you know, if you're a hardware company, you have a pretty big agenda to not have to recall hardware or be liable. If you're a software vendor, you'd like to get your fixes out, ideally first. If you're a competitor, you know, we saw AMD trying to use this for competitive advantage at the beginning, even though they weren't actually, as far as I can tell, any better than Intel, but they were, you know, there were some ambiguous statements that they put out that were misinterpreted by people, one way to put it. So we don't have a playbook here. It'd be great to think about what that ought to be. Well, we're not in the middle of an absolute crisis and running around like chickens with our heads cut off. I think that the direction that we need to go as an industry, though, is we need to stop trying to build one processor architecture that's great for playing video games and doing wire transfers. We need to build architectures where there are cores and software stacks designed for security that can be slower, they can be simpler, and then we need separate ones optimized for performance. I don't see a scenario where we throw away the performance. I also see absolutely no scenario where we get the complexity of our processors and operating systems down to a scale where we're able to cope with the complexity. And we see some systems that are built with this philosophy already, like the Enclave in Apple's iOS devices. The TPM doesn't work great in PCs, but it's kind of that philosophy a little bit. The hardware cores that the Rambus cryptography research team builds also follow exactly this philosophy. And this kind of approach where you have the most important things in a place that's designed for security and that can sit next to something that can play your video game for you doesn't necessarily give you the absolute best of both worlds, but it gives you a way that you don't have to throw anything away. And as we're in a world where transistors are becoming exponentially cheaper, there's not really any reason that when you've got a 16-core processor that we can't have one of those cores optimized for security. We already see ARM with their big little strategy having cores that are optimized for power versus performance. So having ones done for security versus performance is not a major stretch. But the question of what would these security optimized cores look like, we have some examples, but I don't think we have a really great understanding of what the full potential of that is. All right, so that's the end of my prepared statements. I will have happy to take any questions. Or if anybody's holidays got ruined because the embargo that was supposed to end on January 9th got released on January 3rd, you're also welcome to complain.
Why haven't we seen like a major bad actor exploit this in some bad, or at least I haven't seen it?
The question is, why haven't we seen a major bad actor exploit this? Well, how many bad actors put out press releases about what they're doing? So the first question is, what are the telltale signs that we might see if somebody was exploiting it? And I've done some work looking at that question and looking at server logs and things. It's not clear that you'd be able to tell. So I think we just don't know. I think Meltdown would have been the most likely thing that would have been exploited because any intelligence agency or adversary finding out about it during the disclosure process would have known it was going to be fixed and would have had no reason to be careful about maintaining the secrecy of that bug. In the case of Spectre, though, we're going to see them. We may have had some already. It's just that you just don't get good feedback about what attackers are doing.
The Spectre exploits actually explore both the branch prediction for uncached data and also then later just read an uncached memory location. So I assume that the first one to read the memory location, the uncached memory location takes almost the same time frame period as the second one, right? So if that's true, how can the first branch prediction to hide the time in order to read the second one?
That's a great question. So what basically happens is that the second read goes in flight, and once it's in flight, it finishes. So it doesn't matter that the first one comes in while that's occurring. I also should highlight that there are a bunch of variants of the attack. For example, one where what you're looking at isn't changes to the cache state, but the effects of the cache state going in. There are sort of lots of ways that covert channel between the speculative world and the attacker's world can be done. So if you had a processor that, for example, didn't allow the cache state to be modified by speculative execution, very simple changes to the attack still make it work. So if you're putting a countermeasure hat on, you've got to think much more broadly than just the examples that are in the paper. Ditto if you're writing a compiler or a tool, there are lots and lots of code patterns that lead to vulnerabilities, not just the ones that are in the paper.
Thank you.
Thanks for the talk, Paul's really good. So timing attacks have been done for a long time. There's been a ton of papers published on cache timing attacks, branch predictors. Why has this gotten so much heightened awareness now?
Well, so the problem prior to Spectre, or as people had sort of understood it, was that with cache attacks, they would show you information about the pattern of memory accesses that the program performed. And the prior attacks leveraged that information to find out secrets, which is a super powerful technique. But the addition of instructions that the programmer never would have performed, or the program would never have performed, makes the attack a lot more devastating because you can't build a countermeasure as easily. That said, while they're not newsworthy, the leaks of information through caches and other covert channels between entities sharing hardware especially is a very complicated and serious problem, and one where my recommendations about, for example, not hyper-threading and, if possible, not sharing computers at the same time between trusted and untrusted or different security domains is in part motivated by the problem of cache timing attacks.
So at the end of your talk, you hinted that like Spectre and Meltdown might not be the only one of these sort of like speculative execution-based cache timing channels. So there's a paper published this morning called Drive-by Key Extraction Cache Attacks from Portable Code, which was very similar to Spectre, but maybe might the new type of attack? I was curious if you've seen this paper and know if it's just Spectre that's looking at another new type of attack.
Yeah, so the question is about a paper that came out this morning. I haven't seen it, but this is an area where when I wrote the paper on differential power analysis, I kind of thought that was going to cover a good chunk of the territory, and there have been thousands of more academic papers written on taking that in different directions and filling in gaps and things. I kind of expect this to follow some unpredictable trajectory here. Yes, I certainly expect there to be other forms of it. There are many, many things where I can see that there are covert channels that can leak stuff. There are also forms of speculation that involve, for example, optimizations being done in JITs, where they do things where they'll see, oh, this data doesn't ever seem to change, so I'll make a fast compiled version of the function where that's a constant, and then panic and go do a recompilation when that changes. So things that are, right now, a lot of the attacks assume that there isn't speculation being done on the data, but I actually think there are a bunch of places where there is. So yeah, it's going to be messy. I think all of this starts exposing microarchitectural details that many people, I think myself included, wish we didn't have to think about.
So the question for you on the, say one fix would be not to load that illegal value into the speculative register. Would you still have an attack then, or would that be one fix?
Right. So the question is, can you avoid the speculative load, and solve the problem through doing that? And the answer is basically, if most of the problem goes away if you stop that initial speculative load that does the out-of-bounds memory access. But the performance impact from not doing that is pretty substantial, because it means that as soon as you go into speculative execution mode, you're not allowed to read from memory. And also you have to be careful. It's not just enough to not change the cache state, because if the performance of that read, or the behavior of that read, is going to change based on whether the thing you were, the second read will depend on what the cache state was coming into that. So there's a whole bunch of kind of matrices of ways that you can get the improperly read information in, whether it's coming from the stack, coming from memory, coming from a register. So like in the case of a cryptographic routine where an interrupt goes off, you've got sensitive stuff sitting in registers. Then there's a question of what's the way that gets transferred into a covert channel, and then what's the way that it gets read out from that covert channel. And all of those kind of parts of the puzzle have lots of variations attached to them that are possible.
So just thinking about ASLR, so that's actually just a probabilistic way of distributing the code in a very large address space to reduce the probability of that being found. So I don't think this is a fix, but could a mitigation be basically putting all our code through virtual machines? Not that immediately translate to native code, but basically you run like a bytecode or something like this, and then that gets turned into JITted code, which still runs fast. But now we have one more layer of interaction between what the code is running and what the JIT is doing, and that just sort of mitigates, perhaps.
I'm not a big fan of the kind of piling CRUD on type of countermeasures, and ASLR in some ways is an unsound approach. It's one that's kind of probabilistic, but it makes your addresses become secrets in ways that haven't worked very well. And just to take the example of the physical memory cache is tied to the physical addresses. The branch predictor is working on virtual addresses. So the learning in the branch predictor leaks information about the virtual addresses. The thing going on in the cache leaks information about the physical addresses, and you can put those two together to break techniques like ASLR. Using things like a JIT, don't necessarily help you a lot. I mean, if you look at the JavaScript example I gave, or anytime you're writing source code that's going to go through a compiler, there's a certain amount of unpredictability about what that compiler is going to do. But attackers are pretty adept at working around a lot of that. And if you take that combined with the fact that you've got a lot of other side channels around things like caches, hard for me to immediately see that you're going to get a lot of, you're not going to get a crisp explanation of why you're protected, but you're going to do a great deal of work. And what you really want are techniques where you do a small amount of work and you get certain that you've solved the problem, a sound countermeasure. Because we've not had such good luck with unsound ones. And you can see area, things like non-execute bits, and that leads to attacker innovations, like the need to do things like return-oriented programming. But it would probably have been better to try to build systems where the attacks were prevented rather than, I'm going to use the word mitigated in the sense of some of the mitigations that are being put out for Spectre.
Okay, I have a question about TLB address checks, and can TLB address checks be more aggressive in stopping these speculative memory accesses? That's one question. And the second question is about memory encryption technologies such as Intel SGX. So would that solve at least some of these problems?
So, well, I think I'm going to take the first question about address checking, and I think there are scenarios that don't look like just minor tweaks to the way the TLBs work, but it could be pretty interesting. Like there's an initiative called Cherry, where instead of having pointers, you have objects that are called capabilities that basically give you the right to read and or write to some base address and length of memory, and an access that goes outside of that isn't going to be permitted at all. So if you have strict bounds checking, that solves at least certain categories of the problem. Not necessarily all of them, because you might have a big array of which pieces are authorized to be accessed and pieces are not. But at least it's a step toward countermeasures. The other question, so I think there's work to be done there. It's something that all of the processor companies are looking at, but what form that ultimately takes, I think, is going to be evolve over some period of time. The other question was about the implications for SGX, and I know there's some researchers that are looking at exactly that question. I haven't done any tests using SGX, so I don't have any direct results there, although it does seem like the branch predictor used in SGX is the same as the branch predictor used elsewhere, and at least pre the latest microcode updates, there wasn't wiping of the branch predictor state on context switches. I suspect that might be a logical thing to change through microcode updates, but so I think the implications there are somewhat TBD still.
You mentioned that even a processor doesn't allow its cache state to be modified in speculatively. It is still possible to perform the attack. So can you talk more about this?
Yeah. So let's say that second memory lookup, the one where I'm reading from array 2 in the example, doesn't change the cache state. But let's assume that instead what the attacker going into that function is going to have, let's just say one location in array 2 in the cache, and all the other ones not cached. So if that read from array 2 during speculative execution mode reads from an address which is cached, it'll blast right through it and execute additional operations speculatively following that. If it's not cached, well, then it has a different, it may well get stuck or something different will happen, and the result won't be known for a significant period of time, and probably won't even be known until the whole speculative execution unwinds. So if you imagine that the instruction after that, after the read from array 2, reveals something, like it uses the ALU or it reads something or changes anything that I can detect at all, that then can create my covert channel. That's just one example. Again, there are many different ways that covert channels can appear and be exploited in systems. And going back even to the 70s and perhaps 60s, there were researchers who were agonizing over these problems and decided roughly that they were intractable. It's just that people hadn't realized that there existed these covert channels between instructions that weren't supposed to be executed and other instructions, which is what really the only thing that this new research adds.
Actually, we realized that. We didn't realize how controllable they were.
Okay, comment is they may have been realized but not controllable.
All right, one more question?
Is GPU impacted?
I think some of the GPU companies have said that they do have Spectre issues. I would expect any fast processor to be impacted, because if you weren't doing speculative execution, you were wasting performance opportunities. And you might do that if you want your processor to be small, but GPUs aren't small. So I assume so, but I don't want to name any names just because I'm not sure what's public.
Okay, thanks, Paul.